Okay, this is a sort of classic conservation of energy problem where we have a roller coaster. In this case, it's starting at a height of 20 meters. It's going to come all the way down to B, which I tried to show there is basically 0 meters higher, that's the ground. And then it's going to come back up to a height of 10 meters. And we're going to determine the speed at point B and point C. The best way to do this problem is to just sort of recognize that really it's two problems, so we'll deal with each problem separately. Let's first find what the speed of it is at point B. I forgot to write here, but we're going to assume that the roller coaster starts from rest at the top of that top hill. So, at point B, what's happened here is that in energy 1, it has gravitational potential energy. And all of that is going to be converted in E2 for point B, since going down to a height of 0, to all kinetic energy. So by the conservation of energy, this is assuming this roller coaster has no friction or anything like that, E1 equals E2. What that means is that my gravitational potential that I started with is going to be kinetic in the final situation. My formula for gravitational potential energy is mgh, and for kinetic energy is 1/2 mv squared. The masses cancel out. So, and mass can equal 0. We don't know what the mass of this roller coaster is, but it's not 0, so that's fine. G is 9.8 meters per second squared. Newtons per kilogram if you want, but meters per second squared is fine. Times 20 meters is equal to 1/2 times the velocity of my coaster at point B, which is what I'm trying to find. So 20 times 2 times 9.8 equals 392 meters squared per second squared, and that's VB squared, and then we'll square root both sides. And VB is going to be equal to 19.8 meters per second. So that's how fast it gets going at the bottom of that hill. And that's the first part. Now at point C. So let's deal with point C. Don't know what happened there, but that's okay. Oh, all kinds of trouble. Point C. At point C, it's a little bit trickier. I can compare all the way back to point A, or I can compare to point B. But since I was given the information at A, it's probably safer to go back to that information under the whole we don't want to carry errors around if possible. E1, my initial energy, is going to be all gravitational potential energy. It's at the top of that 20-meter hill and it's not moving. E2 in this case is going to be a little bit trickier. See, now it's up 10 meters and it's moving for point C. So what that means is that I have some gravitational potential energy. I'm going to call it EG2, and then I'll call this one EG1 just to keep them separate. And it's going to have some kinetic energy. So using the law of conservation of energy, where I recognize that the energy 1 is equal to the energy 2, what that means then is that I've got this EG1 initially, and that's getting converted into a gravitational potential energy that'll be slightly smaller, and what's left over is going to be kinetic. So here I have mass times gravity times height 1, which will be the 20 meters. Here I have mass times gravity times height 2, which will be the 10 meters. And some of that gravitational potential energy will be left over for my speed at C. There's mass in every term. And now, again, the mass can equal 0. I'm going to multiply by 9.8 meters per second squared. By the way, for kinetic energy and gravitational potential energy, there's always going to be a mass term, and so this mass is always going to be canceling out. But we need to be careful with two basic things. As soon as we add stuff like springs, they won't have a mass term, so we can't do it. And when we add work to this equation, if we allow the energy to change, it doesn't have a mass term either, and that's going to screw up the canceling out of mass. So careful, right now we can get away with it, but later when we add more complexity to these problems, we won't be able to. So 20 times 9.8 is 196 meters squared per second squared. On this side I have 98 meters squared per second squared, and I got 1/2 times VC. Oops. VC squared. Bring the 98 over, that'll make 98 meters squared per second squared equals 1/2 VC squared. And then multiplying both sides by 2. And then square rooting. And the square root of 196, I think it's 14. Yeah, 14 meters per second. So that'll be my speed at c. So there you go. Here we have a situation where all of the gravitational potential energy was converted into speed. And here, some of that gravitational potential energy stayed as gravitational, and the remainder went to speed.